Question 9.2 from the homework: in which of the following molecules can you confidently predict the bond angles around the central atom, and for which would you be a bit uncertain? So to answer this question, we worked through a similar series when we looked at methane, ammonia, and water. We talked about the effect of lone pair electrons on the geometry. So we basically need to put together the Lewis dot structure for all these compounds to figure out what compounds might have some lone pair electrons that could change geometry. So all I did quickly was add up all the valence electrons we have to work with just to save some time in putting together those Lewis structures. So carbon tetrabromide, we're going to have 4 electron domains, and so we're going to be tetrahedral, and our bond angles should be 109.5. So for this one, I would expect the bond angles to be your normal predicted bond angles of 109.5. There's nothing that would change that. Let's see, I just signed 8 electrons there, plus 24 electrons there, so 8 plus 24, 32 electrons. So all those are all set. Look at the boron trichloride next. Boron, the 3 chlorines, and then that's 6 electrons, and then filling the octets of chlorine would assign 18 electrons. 6 times 3 is 18, plus the 6 electrons from the bond. That would give us 24 electrons, and we've assigned everything here. The tellurium bromide, we've got 34 electrons, so the Lewis structure for that, we're going to be a little bit different in that we have our 4 bromines, so there's 8 electrons there. Once we fill the octets for all the bromines, we're going to use 24 more electrons, so 24 and 8, that's 32. And that's going to leave us with 2 electrons remaining. So we have 34 total valence electrons to assign. So those 2 remaining electrons would go right here on tellurium. And what this does is, right, non-bonding electrons take up more space than bonding electrons. So here's that orbital with those 2 lone pair of electrons. What's going to happen is they're going to repel, they're going to push this tellurium bromine bond and this tellurium bromine bond a little bit farther away than they should be, and they would also push these 2 tellurium bromine bonds a little bit farther away. So instead of expecting this bond angle to be 180, it might be 181 or 182. We're basically pushing these bromines a little bit farther away, and then these 2 bond angles here, instead of being 120, these 2 bromines, they might be 118 or 116 because they're being pushed closer together. So the tellurium tetrabromide, yeah, we would expect that to deviate from ideal bond angles. And then for our iodomethane, this one's a little bit different, but it's similar in that yeah, it would be tetrahedral. We'd assign all of our electrons. And again, here, it's not a lone pair of electrons, but iodine, right? Iodine is much, much, much larger than hydrogen. So it's going to take up a lot more space. And so as a result, just to accommodate the space of that iodine, we would push these hydrogens closer together. So instead of being the 109.5 that we'd expect in a tetrahedral arrangement, they're going to probably be closer to 107 degrees or so. So we would expect this one to also deviate from ideal bond angles. And the last one, this is just like water, similar to water in that we've got sulfur, and we've got 2 hydrogens, right? So if we think about that in the tetrahedral, so we've got 4 electron domains. We think about that in the tetrahedral electron domain geometry. We'd expect the bond angles to be 109.5 degrees, but again, these lone pair electrons take up much more space than bonded electrons, so they're going to push these two hydrogens closer together. So this bond angle, instead of being 109, might, like in water, for example, it's 104.5 degrees. So again, because we have extra lone pair electrons here on sulfur, we should expect to find these bond angles to deviate from normal. So that's what we're looking at, are basically, do we have lone pair electrons, and are those lone pair electrons on the central atom able to influence the bond angles we have? And in the case of the iodine, it's just the size of that atom. To accommodate that extra size, yeah, we're going to kind of push these carbon-hydrogen bonds closer together as a result of the size of that iodine.